Hi, I'm Kevin McCarthy, and in today's video we're going to be looking at the precision motion aspects that enable high throughput microscopy. Now, it's worth taking a moment to distinguish high throughput microscopy from the alternative. There's sort of two basic things that can happen. In low throughput microscopy, it's typically a university researcher. There's an entirely different sort of microscopy which requires a very large number of images to be taken. This can easily run from thousands into the millions, and it's not done with a human operator checking through a trinocular eyepiece. It's done totally in an automated fashion. And in that case, throughput is very important. Generally speaking, because the instrument is likely something that's being made over and over and over again by what we would call an original equipment manufacturer, the interest is in making the instrument as compact as possible, as cost-effective as possible. It needs to do exactly what it needs to do and no more. Dover Motion specializes in enabling that sort of instrument with some pretty spectacular stages that are breakthrough. And these would generally be the motion axes in a bespoke instrument that would be dedicated to the particular task that the instrument has to perform. Here we have a pair of our breakthrough Dover Motion SmartStage XY product line. In this case, we have a 150 millimeter travel on the bottom axis and a 100 millimeter travel on the top axis. Generally speaking, samples such as this flow cell are considerably larger than fields of view. Fields of view can be a fraction of a millimeter to several millimeters. So because the sample is considerably larger than the fields of view, we need XY motion. And similarly, especially if the depth of field is very shallow due to high numerical aperture objectives, we have to have a Z focus stage that retains the image in crisp focus as we move across the sample. In addition to the sample that we've shown there, which is a flow cell, other common samples include microscope slides, which may be presented one at a time or in an array of more than one, 4, 8, 16. They can also be fed by a magazine, input and output. Another common sample format is the microtiter plate. These come in 96, 384, and 1536 well variants, where the pitch between wells is correspondingly 9, 4.5, and 2.25 millimeters. Let's take a look at an image that'll show the typical sequence of events when we do what we call sequential field imaging. Now, I should make it clear that there are really two ways that you can approach high throughput microscopy imaging. One, the topic of today's video, is sequential field imaging. That's where you move, stop, take a picture, and repeat. There's an entirely different approach, which is called TDI scanning imaging. That will be the subject of a different white paper and a different video. So let's take a look at what goes on in sequential field imaging, one after the other. So basically, as the blue form, this is, by the way, velocity versus time. And when we get from point A to point B, which might be from one of these wells 4.5 millimeters further to the next well, when we do that motion, the velocity increases and then decreases. We can use a triangular profile. In this case, we're showing an S-curve profile, but the bottom line is the blue period of time is the time within which the stage moves to the next field of view. And it actually has to both move and settle. So when it gets to the new position, it can't be vibrating, it has to stop. As soon as it has stopped, illumination is turned on, and the field is illuminated, and the camera is now acquiring the image. And after some period of time, which depends upon the application, the image is fully acquired, the light is turned off, and under the cover of darkness, we race to the next field of view. Now, there's two things that actually happen during this intermediate phase. They include the XY stage motion, but as we'll see later in the video, they also have a very important fact, which is that the image which was acquired when the illumination was on has to be downloaded during that period as well. So, as I say, during the cover of darkness, as we move to the next field of view, we're also downloading the next image. Another thing that we can address is what strategies we use to reach all the fields in a sample. And typically that's done with a tiling approach in which the upper axis will move the most and the lower axis will simply move between rows. So let's take a look here. This, in fact, is this specific flow cell with 8 lanes. Fluid comes in here and comes out there. And if we can zoom in here, we have image 0. We're looking here at a single one of these lanes. So this little black circle, we're blowing it up. And that one lane, which is, I think, maybe about 5 millimeters wide, we have image 0 in the lower left. And then we move to image 1 and on and on and on, and all the way down to image 217. And then we step over in the lower axis, which has a higher payload mass and doesn't have to move as aggressively. We move over to image 218, reverse direction, and head on down the row to image 435. Continue this all the way to image 2179. So that's 2,179 images on a single lane. There are 8 lanes, and in this particular case, this had to be done in 4 colors for 26 bases. So we're talking millions of images here. And to sort of cue up the audio on this, as you make the high frequency moves down the thing and then you index over in the lower axis, it's sort of like a brrr, chunk, brrr, chunk. And that is the tiling strategy with which we get the entire sample imaged. The smart stage XY that we showed earlier is a direct drive stage. And that is the highest performance way to get linear motion. Another approach would be to use a lead screw or a ball screw. That could be activated by a rotary motor, could be a brushless motor with a rotary encoder, could be a stepping motor open loop. But the bottom line is all of those approaches are incredibly inefficient compared to the very high performance of direct drive. In that case, there are simply magnetic fields that create the motion. It's all under the control of a very tight 20 kilohertz servo loop, and the performance is exceptionally higher. By the way, in addition to lead screws and ball screws, there are also piezo mechanisms. You don't want to get me started on those. They have a host of problems. So basically what this sequential field motion amounts to is get me to the field on time, field of view, and the idea is to get from each one as quickly as possible. And you can also describe what needs to happen as 2 key attributes: move really fast and then hold really still. If we're not holding really still, and we're talking at the 100 nanometer or below level, if we're not holding really still, then these microscopy images are going to be blurry, and that is unacceptable to get the data that's required. So it's move real fast, hold real still, rinse and repeat.